The Deutz F6L912 engine might just be the most misunderstood power plant in industrial history. You've probably heard mechanics talk about these German workhorses with a mix of respect and confusion, wondering why anyone would still run an air-cooled diesel when water-cooled engines dominate every shop floor. But if you thought these engines were just outdated tractor motors, you're in for a surprise. In the next few minutes, you'll discover 20 secrets about the F6L912 that even seasoned diesel mechanics don't know, including one fact about these engines that's so bizarre. It changed how an entire industry thinks about cooling systems. F6L912, code decoded. That cryptic model number isn't just random letters and numbers thrown together by German engineers. The F means four-stroke, the 6 indicates cylinder count, L stands for Luftgekühlt, which is German for air-cooled, and 912 represents the series. This naming system hides the engine's key specifications in plain sight, and once you crack the code, you can decode any Deutz engine model instantly. What makes this particularly clever is that Deutz used this system across their entire lineup, creating a universal language that mechanics worldwide could understand without translation. The 912 series specifically was born in 1959 and ran through various evolutions until 2007, making it one of the longest-running engine designs in diesel history. Most people assume complex model numbers are just bureaucratic nonsense, but Deutz engineers embedded critical service information right in the name. If you see an F6L913, that's the turbocharged version. An F4L912, same engine family but with 4 cylinders. This coding system was so effective that Chinese manufacturers who licensed the design kept the exact same nomenclature when they started building clones in the 1980s. No radiator at all. Here's where the F6L912 breaks every rule you learned about diesel engines. While your typical diesel has a radiator, water pump, thermostat, hoses, and coolant, the 912 has none of that. Instead, it uses a massive axial fan and deeply finned cylinder barrels to dissipate heat directly into the air. This isn't some cost-cutting measure. It's brilliant engineering that eliminates the single biggest failure point in most diesel engines. Think about it. No radiator means no coolant leaks, no water pump failures, no frozen blocks in winter, no boiling over in summer. The cooling system literally cannot fail because it doesn't exist in the traditional sense. That big fan you see on the front? It moves up to 10,000 cubic feet of air per minute, creating a hurricane of cooling that flows through precisely designed shrouds and baffles. The cylinder fins aren't decorative either. Each fin is calculated for maximum surface area and heat transfer, with the rear cylinders getting progressively deeper fins to compensate for the warmed air flowing over them. In dusty environments where radiators clog daily, these engines just keep running. In freezing conditions where coolant turns to slush, they fire right up. In marine applications where salt water eats through heat exchangers, they laugh at corrosion. Big 6 punch. The bore and stroke dimensions of 102 millimeters by 132 millimeters might not sound impressive until you do the math. That's 6.47 liters of displacement from a remarkably compact package. To put that in perspective, that's bigger than the legendary Cummins 5.9 liter that powers millions of Dodge Ram trucks. But the Deutz achieves this in a smaller, lighter package, thanks to its modular cylinder design. Each cylinder displaces 1.08 liters, and because they're individual jugs, the engine block itself is surprisingly small. The long stroke design creates massive leverage on the crankshaft, which is why these engines develop their peak torque at such low RPMs. We're talking about pistons that travel over 5 inches on each stroke, creating the kind of low-end grunt that makes modern high-revving diesels feel anemic. The combustion chambers use a direct injection design with a toroidal piston bowl that creates excellent fuel-air mixing despite the relatively low injection pressures. This big displacement from a physically small engine made the F6L912 perfect for applications where space was tight but power demands were high. Mining equipment, generators, pumps, and marine applications all benefited from this unique combination of compact size and substantial displacement. Tractor pull torque factory. Specifications list 370 Newton meters of torque at just 1,450 RPM, with 82 kilowatts at 2,500 RPM in standard tune. But here's what those numbers really mean in the real world. That torquey peak arrives just off idle, meaning these engines develop their maximum pulling power almost immediately. Unlike modern diesels that need to spool up turbos and build boost pressure, the naturally aspirated 912 delivers instant, predictable power. This torquey curve is so flat, it's almost a straight line from 1,200 to 2,000 RPM. You could lug this engine down to walking speed in high gear, and it would just keep pulling without complaint. That's why you'll find these engines in applications like rock crushers and pump drives, where the load can spike instantly and unpredictably. The power might seem modest by modern standards, but remember, this is continuous duty rated power. These engines can produce their rated output 24 hours a day, 7 days a week, for years on end. Many operators report running them at full load for 10,000 hours between overhauls, something that would destroy most modern engines. The secret is in the conservative design, with low piston speeds, moderate combustion pressures, and massive bearing surfaces that distribute loads evenly. Swap A jug design. This might be the most revolutionary feature of the F6L912 that nobody talks about. Each cylinder is completely self-contained with its own barrel and head as a single unit. If cylinder number 3 develops a problem, you don't rebuild the entire engine. You unbolt that one cylinder, slide it out, and bolt in a replacement. The whole job takes about 2 hours. Think about the implications of this design. A construction company in the middle of nowhere can carry spare cylinders instead of spare engines. A marine operator can fix a dropped valve at sea without dry docking. A mining operation can swap a damaged cylinder during a lunch break. This modular design also means you can upgrade individual cylinders as improved versions become available. Early 912 cylinders had different port timing and compression ratios than later ones, and you can mix and match to some degree. The cylinder base has precision-machined registers that ensure perfect alignment every time. There's no guesswork, no special tools required beyond basic hand tools. The head bolts thread into the cylinder barrel, not the block, so you never have to worry about pulling threads out of the crankcase. This design was so successful that Deutz used variations of it across their entire air-cooled line, from single-cylinder units to V12s. Old-school tough valve train. In an era of overhead cams and 4 valves per cylinder, the F6L912 sticks with push rods, rocker arms, and 2 valves per cylinder. But before you dismiss this as antiquated, consider why Deutz never changed this design over nearly 50 years of production. The aluminum cylinder heads use a simple overhead valve design with 1 intake and 1 exhaust valve. The push rods are massive compared to automotive engines, nearly ½ an inch in diameter, making them virtually indestructible. The rocker arms pivot on hardened shafts with pressure lubrication, not the stamped steel rockers you'd find in cheaper engines. Valve adjustment is dead simple, with lock nut adjusters that stay put for thousands of hours. The camshaft lives low in the block where it gets constant oil bath lubrication and drives the valves through short, stiff push rods that minimize flex and wear. This system might not rev to 5,000 RPM, but it doesn't need to. At the engine's 2,500 RPM red line, valve float is physically impossible. The valve springs are so conservatively rated, they maintain full pressure even after 20,000 hours of operation. Valve guides are replaceable without removing the heads, another nod to field serviceability. The exhaust valves use steelite facing for extreme durability, and the seats are induction hardened to resist recession even with today's low-sulfur fuels. Purely mechanical fuel, the Bosch inline PES 6 A-type injection pump on these engines represents the pinnacle of mechanical fuel injection. No electronics, no sensors, no computers, just precision mechanical components that meter fuel with repeatable accuracy. This pump uses a camshaft-driven plunger system where each cylinder gets its own pumping element. The mechanical governor uses flyweights and springs to maintain speed regardless of load, responding instantly to changes without any electronic lag. Starting enrichment happens automatically through a mechanical device that advances injection timing and increases fuel delivery when cold. The injection lines are all exactly the same length to ensure simultaneous injection timing, and they're made from seamless steel tubing that can handle the 1,000+ bar injection pressures. What's remarkable is how precisely these mechanical systems work. The governor can hold engine speed within plus or minus 10 RPM under varying loads, better than many electronic systems. The injection pump can be rebuilt on a bench with basic tools, and timing is set with simple marks rather than computers. Individual pump elements can be calibrated on a test bench to ensure each cylinder gets exactly the same fuel delivery. This mechanical simplicity means these engines can run on almost any diesel fuel, from modern ultra-low sulfur to waste oil blends that would destroy a common rail system. Triple PTO choices, power takeoff options on the F6L912 are almost unlimited. You can pull power from the flywheel housing, the front damper, through V-belts, or via accessory gear drives. This flexibility made these engines incredibly versatile for OEM applications. The flywheel PTO uses a spline coupling that can handle the engine's full torque output, perfect for driving pumps or generators. The front PTO options include both belt drives and direct gear drives, with some versions offering multiple PTO pads for running several accessories simultaneously. The timing gear train has provisions for driving hydraulic pumps directly from the camshaft gear, ensuring precise speed relationship with engine RPM. Many industrial versions came with SAE standard PTO, mounting faces that accepted industry-standard pumps and motors. The beauty of these multiple PTO options is redundancy. If a belt-driven accessory fails, you might have the same function available through a gear-driven option. Marine installations often use one PTO for propulsion and another for hydraulics, all from the same compact engine. Some specialized versions even had PTOs on both ends, plus a belt-driven alternator powering 3 different systems simultaneously. The engine's massive torque at low RPM means these PTOs can drive high-load accessories without lugging the engine. Oil does double duty. The lubrication system on these engines goes far beyond just keeping bearings happy. An external engine oil cooler was standard on most applications, using engine oil to help with thermal management. But the really clever bit is the oil bath air filter system. Instead of paper elements that clog with dust, these engines use a bath of engine oil to trap particles. Incoming air passes over the oil surface, where dust and debris stick to the oil film. The air then passes through a mesh element that's constantly wetted with oil, providing a second stage of filtration. This system is so effective it can handle environments that would clog a paper filter in minutes. The oil capacity is generous too, with most F6L912s holding 15 to 20 liters of oil. This large volume means the oil runs cooler and stays cleaner longer. The oil pump is gear-driven and delivers massive flow even at idle speeds. Oil pressure typically runs 60 to 80 psi, ensuring positive lubrication to every bearing surface. The crankshaft has drilled passages that deliver oil to every bearing journal, and spray jets cool the piston undersides. Even the valve gear gets pressure lubrication through drilled passages in the rocker shafts. Many operators run these engines 500 hours between oil changes in clean conditions, far longer than modern engines allow. Fan belt fail-safe. Here's a safety feature that shows just how thoroughly Deutz engineers thought through air-cooled engine design. Many F6L912 installations include a belt brake switch that monitors cooling fan belt tension. If the belt breaks or goes slack, this switch immediately cuts fuel to prevent catastrophic overheating. On a water-cooled engine, you might drive several miles before noticing the temperature gauge climbing. But on an air-cooled engine, losing coolant airflow means cylinder temperatures can spike to dangerous levels within minutes. This simple switch has saved countless engines from destruction. The system works through a spring-loaded arm that rides against the belt. Normal belt tension holds the switch contacts open. If the belt breaks, the spring pulls the arm back, closing the contacts and triggering either a fuel cutoff solenoid or an alarm, depending on the installation. Some versions even had automatic engine shutdown with a manual override for emergency situations. What's clever is that this system also detects when belts are getting loose before they fail completely. Operators learn to check belt tension whenever they hear the warning alarm, preventing unexpected failures. The switch is adjustable for different belt tensions and configurations, making it adaptable to various installations. Cold start party trick. While most diesels rely on glow plugs in each combustion chamber, many F6L912 engines use a completely different cold start system. The intake manifold has a flame start heater that creates a small fire inside the intake tract, preheating incoming air before it reaches the cylinders. This system starts with a glow plug that ignites a small amount of diesel fuel in a combustion chamber built into the intake manifold. The resultant flame heats the intake air to several hundred degrees, ensuring easy starting even in Arctic conditions. It's like having a tiny furnace inside your engine. The advantages over traditional glow plugs are significant. There's only one heating element to maintain instead of 6. The system works even if compression is marginal, since it's heating the air rather than relying on compression heat. Starting is almost instant once the flame heater lights, compared to waiting for glow plugs to heat up. The flame heater also helps during warm-up, continuing to heat intake air until the engine reaches operating temperature. Some operators in extreme cold climates run the flame heater continuously at low load to maintain intake temperatures. The system is so effective that engines have been started at -40 degrees without any other starting aids. The only downside is a slight increase in fuel consumption during the preheat cycle. Dust-proof tinware. Those coolant shrouds and baffles around the cylinders aren't just bent metal. They're precisely engineered components that direct cooling airflow exactly where it's needed. Remove one panel or let debris block the fins, and cylinder temperatures can spike dangerously within minutes. Each shroud is designed to create specific pressure differentials that force air through the cylinder fins at high velocity. The baffles between cylinders prevent hot air from one cylinder from heating its neighbor. Even the small deflectors around the exhaust ports are critical, keeping exhaust heat away from the intake side of the head. Deutz spent thousands of hours in wind tunnels perfecting these airflow patterns. The shrouds create a Venturi effect that accelerates air through the narrowest passages where coolant is most critical. Missing or damaged shrouds don't just reduce coolant, they can completely disrupt the designed airflow patterns. Many engine failures blamed on air coolant were actually caused by missing or incorrectly installed shrouds. The tinware also serves as a safety barrier, keeping hands and tools away from hot cylinders and moving parts. Some versions had special shrouds with inspection ports for check and valve adjustment without disassembly. The shrouds are typically made from heavy-gauge steel with reinforced edges to resist damage. Paint color even matters, with the black crinkle finish designed to radiate heat better than smooth paint. 2 912 generations, not all F6. 912 engines are created equal. There's a major split between early engines built before 1997 and later versions that meet stricter emission standards. The differences go far deeper than just bolt-on accessories. Early engines used flat-top pistons with a simple bowl design and lower compression ratios around 17:1. Later engines got revised pistons with a more complex combustion chamber shape and compression ratios up to 19:1. The cylinder heads changed too, with different port timing and valve sizes. Injection systems evolved from the older PES pumps to newer designs with different cam profiles and delivery rates. The fuel injectors themselves are completely different, with later versions using multi-hole nozzles for better atomization versus the single-hole or dual-hole nozzles in early engines. Mixing parts between generations can cause serious problems. An early piston in a late cylinder head won't have the right compression ratio. Late injectors in an early pump won't deliver the correct fuel quantity. Even seemingly identical parts like connecting rods had subtle changes in weight and balance. The crossover happened gradually, with some transition engines using mixed components. Serial numbers are critical for ordering correct parts, and many suppliers don't realize there are two distinct versions. Smart rebuilders keep early and late cores separate to avoid expensive mix-ups. Shim set liner height. Here's a critical detail that trips up even experienced mechanics. The cylinder liner protrusion above the block deck isn't fixed. It's set with precision shims at the base of each cylinder. Get this wrong, and head gaskets will never seal properly. Each cylinder needs to protrude exactly 0.08 to 0.12 millimeters above the block surface. Too little protrusion, and the head gasket won't compress properly. Too much, and you risk cracking the cylinder head or distorting the fire ring. Deutz provides special depth gauges and shim sets for setting this correctly. The process requires removing each cylinder, measuring the liner seat depth in the block, measuring the cylinder height, and calculating the exact shim thickness needed. Shims come in increments of 0.05 millimeters, and you might need to stack multiple shims to get the exact dimension. Temperature changes affect these measurements too. A cold engine will show different protrusion than one at operating temperature due to differential expansion between the aluminum pistons and iron cylinders. Many head gasket failures blamed on the gaskets themselves are actually caused by incorrect liner height. The gasket fire rings are designed for a specific compression range, and being off by just a few thousandths can cause chronic sealing problems. Experienced rebuilders check and document liner protrusion for each cylinder, creating a map for future reference. SIPs for its size. For a 6.5-liter naturally aspirated diesel, the F6L912 is surprisingly fuel efficient. Specific fuel consumption around 225 grams per kilowatt-hour was competitive with much more complex engines. At part load, these numbers get even better. The secret lies in the efficient combustion chamber design and precise mechanical injection. The long stroke creates high compression temperatures that ensure complete fuel burn. The mechanical injection system delivers fuel at exactly the right moment with no electronic lag or variation. There's no turbo lag eating fuel during acceleration, no complex emissions equipment creating back pressure. In stationary applications running at constant speed, operators report fuel consumption as low as 200 grams per kilowatt-hour. That's better than many modern electronic engines achieve. The mechanical governor holds speed precisely without the hunting and surging that wastes fuel in electronic systems. Generator operators love these engines because fuel consumption is predictable. You can calculate runtime from tank capacity with remarkable accuracy. The engine burns the same amount of fuel per kilowatt-hour, whether it's brand new or has 10,000 hours on it. This consistency makes operating cost calculations simple and reliable. Many operators report that rebuilding injection pumps and injectors returns fuel consumption to like-new levels, something electronic systems can rarely match. Forged where it counts. The bottom end of these engines is built like a bank vault. The crankshaft is drop-forged from high-grade steel, with bolted counterweights that can be individually balanced or replaced. Main bearing journals are massive, spreading loads over large surface areas for exceptional durability. The connecting rods are forged steel I-beam designs with a cross-section that provides maximum strength with minimum weight. Rod bearings are oversized compared to the power output, ensuring they never see excessive loading. The pistons use oil cooling jets that spray directly onto the underside of the crown, critical for managing thermal loads in an air-cooled engine. The engine block itself is a massive iron casting with thick walls and extensive ribbing for strength. Main bearing caps are cross-bolted in addition to the vertical bolts, preventing capwalk under heavy loads. The crankcase is designed to handle the side loads from the long stroke without flexing. Even details like the oil pan are overbuilt. Instead of stamped steel, you get a cast aluminum pan with coolant fins and massive capacity. The pan gasket surface is machined flat and uses a proper gasket, not just silicone sealant. This robust construction is why you'll find 30-year-old engines still running original bottom ends. The forged components can handle occasional overloads that would destroy cast parts. Operators report running these engines with failed governors at overspeed without throwing rods, testament to the strength built into every component. Still earns its keep. While you might think air-cooled diesels are ancient history, F6L912 variants were still being offered into the 2000s to meet EU Stage 2 and US Tier 2 emission standards. These aren't museum pieces. They're working engines preferred in specific applications. In underground mining, the absence of coolant means no glycol contamination if a hose bursts. In desert operations, there's no radiator to clog with sand. In Arctic conditions, there's no coolant to freeze. In marine use, there's no raw water cooling system to corrode. These modern variants got updated injection systems for cleaner burning, improved air filtration, and better governor control. But the basic architecture remained unchanged because it works. The engines meet emission standards through precise combustion control rather than add-on equipment. Many countries with less stringent emissions requirements still prefer these mechanical engines. They can be repaired with basic tools by mechanics who learned their trade decades ago. Parts availability remains excellent, with both OEM and aftermarket suppliers offering everything from gaskets to complete cylinder kits. The Chinese-built versions under license from Deutz continue to evolve, with some featuring electronic governors and common rail injection while maintaining the air-cooled architecture. It's a testament to the fundamental soundness of the design that it remained viable for nearly half a century. Built far beyond Cologne, Deutz licensed F6L912 production to manufacturers worldwide, but the most significant was to China's Beinei Corporation. This wasn't just a parts deal, it was complete technology transfer including tooling, drawings, and manufacturing processes. Today, you can buy brand new 912 engines built in China. Chinese production started in the 1980s when China needed reliable industrial power and had limited technical capability. The 912 was perfect, mechanically simple but thoroughly proven. Beinei didn't just copy the engines, they continued development, creating versions Deutz never built. You can now buy 912 variants with electronic control, common rail injection, and even meeting Euro 5 emission standards. The global availability of parts is staggering. Whether you're in South America, Africa, or Asia, someone nearby probably stocks 912 parts. The engines became so common in developing countries that entire support industries grew up around them. This worldwide production also created interesting variations. Indian manufacturers build special versions for agricultural pumps. Brazilian companies make marine-specific variants. Russian builders created Arctic versions with special alloys for extreme cold operation. The interchangeability is remarkable too. Chinese pistons fit German blocks. Indian-made injection pumps bolt onto Brazilian engines. This global parts network ensures these engines will remain viable for decades to come. It's possibly the most successful technology transfer in diesel engine history. Boat-friendly coolant, marine applications showcase the brilliance of air coolant. While most marine diesels need raw water pumps, heat exchangers, zinc anodes, and constant maintenance to fight corrosion, the F6L912 just needs ducted air. No seawater contact means no corrosion. Mounting these engines on deck eliminates most cooling concerns. The engine room just needs adequate ventilation, not complex plumbing. The air intake can be ducted from outside, ensuring cool air regardless of engine room temperature. The exhaust system is simpler too, without water-cooled manifolds to corrode. Many commercial fishing boats run these engines precisely because they eliminate coolant system maintenance. There's no impeller to change, no heat exchanger to rot out, no risers to replace. The engine either runs or it doesn't, with no gradual degradation from corrosion. The weight savings are significant too. No raw water system means no heavy bronze pumps, no water-filled exhaust components, no keel coolers. This can mean hundreds of pounds saved in smaller boats. The reliability improvement is even more important. Water pump failures are a leading cause of marine engine damage. Eliminate the pump, eliminate the risk. Operators report running these engines in salt spray conditions for decades with nothing more than regular washing to prevent external corrosion. The cooling fins actually help here, shedding water quickly and preventing pooling that causes corrosion. ID plate matters. That stamped aluminum plate on the crankcase contains more information than most people realize. Beyond the serial number, it encodes the exact build specification, emission certification, and even the factory where it was built. Understanding these codes can save thousands in parts costs. The serial number prefix indicates the engine family and generation. A serial starting with 29 indicates a different specification than one starting with 32, even though both might be F6L912 engines. The suffix letters indicate specific customer adaptations or market requirements. The build date code tells you which generation of parts to order. An engine built in 1995 uses different pistons than one built in 1999, even though they look identical. The emission certification stamps indicate which fuel system calibration was used. Some plates include a build sheet code that Deutz dealers can reference to find the exact parts list for that specific engine. This includes details like injector nozzle specifications, governor spring rates, and even paint codes. Aftermarket rebuilders often ignore these codes and wonder why their rebuilt engines don't perform correctly. Using the wrong generation pistons might only cost 20 horsepower, but that's significant in a 100 horsepower engine. The plate also indicates which optional equipment was factory installed. Some engines had provision for accessories that weren't installed, and the plate tells you which mounting bosses are drilled and tapped versus which are just cast blank. That's all for today, folks. If you enjoyed this video, don't forget to subscribe and hit that like button so you don't miss the next one. See you there.